three parts. So in the first is we'll discuss graphs and we'll get our hands dirty with networkx for graphs. Second thing, we'll delve deeper into paging algorithm, which was developed by Google, and since then it has found its usage currently. Uh, in third part, basically we'll be talking about how we can apply PageRank on NLP tasks like key phrase extraction or summarization. Okay, so let's get started. Quick definition of graphs. So whenever we talk about graphs, we have two things. One is the nodes, vertices, and another is edges. So edges are the links that connects the nodes. Uh, Based on whether the edges are directed or undirected, we have two types of graph. So when the edges are directed, it's directed graph, and when the edges are direction doesn't matter, it's undirected graph. So let's say in Facebook, when you are friends with people, right? So their direction doesn't matter. If I'm your friend on Facebook, then you are also my friend on Facebook. So there we can model that relationship with an undirected graph. But when we are on Twitter, then let's say I follow you, that does not mean you also follow me, right? So there the edges has to be directed, and that is better modeled with a directed graph. So in order to create graph, so networkx library has this thing. Digraph is for directed edge. So let me just run it. Yeah. So here we have like four edges and four nodes, and this is how we have connected the nodes. So this is an example directed graph, and networkx also provides us a way to draw it so that we can visualize it whether it is created as per our expectation. So this is how a graph is created. Now there are different operations that we can apply on graph. So we can actually enumerate the number of nodes. So 1, 2, 3, 4 are the four nodes. We can enumerate the edges that are there in the graph. So just by g1 dot edges. Uh, if you are interested in the out degree, we can just run this function and we get the out degree. So node number one is connected to, let's say, one outgoing edge, two is connected to zero outgoing edges. As you can see here, there is no outgoing edge out of two, so its out degree is zero. Likewise, three has two outgoing nodes, so its out degree is two. So other than that, there are a lot of things which we can do. One is node connectivity, how a node is connected to, let's say, another nodes. So this is defined by how many vertices you have to remove so that there is no path between two nodes. So for example, for one and two, right? So only one node needs to be removed and they will be disconnected, right? So more connected a graph is, then there are more than one ways to reach one node to another. And as a consequence, there will be more number of nodes that will need to be removed in order to eradicate the path between two nodes. So that is covered in node connectivity. Uh, we can also find out what is the shortest path between two nodes. So that is covered by this. So let's say that between 4 and 2, uh, let's say we want to go from 4 to 2, then there is no other way other than going through 1. So the path will be of length 2, and that shortest path is shown by this. So G1 is a graph, source node, target node, and we get to see the shortest path. That is between the 4 and 2. Now, this is just a tip of the iceberg, what networkx offers. But if you go and check out the documentation, then there are like huge number of algorithms that are already implemented in networkx. For example, clustering, connectivity, cuts, bipartite graphs, all that we have studied in our courses. Cycle detection, walks. All this is like already available, and their documentation is also neat. So I encourage you check out this documentation. But we'll not dwell deeper into what are all the capabilities of networks. We'll focus our attention on one class of algorithms, which is centrality algorithm. So just to confirm, I'm audible clearly, right? You're able to hear me? Okay. So yeah, now we talk about centrality algorithms, and centrality algorithms basically gives the assumption that in a graph there are some nodes which are more important than the other nodes. Okay, so all nodes doesn't hold the same level of prominence in a graph. So you can think of centrality as a measure of prestige, influence, control, or popularity, right? In a graph that a node holds. So सेंट्रलिटी एल्गोरिदम्स का गोल ये रहता है कि उनको एक ग्राफ में हर एक नोड को एक रियल नंबर असाइन करना होता है जो उसकी सेंट्रलिटी को दर्शाता है. So more is that number, more is the importance of uh, that node in the graph. Okay, so this is a function, utility function that we have created. So as a result of this function, what will happen is the graph that will draw, uh, the size of the node will be proportion to its importance based on whatever centrality dictionary we pass to the graph. Okay, so there are different classes of centrality algorithms which we can discuss one by one. So one is degree based centrality. So degree based centrality favors node that have greater number of nodes adjacent to them. Okay, so they reward direct neighborhood. So the formula that network use for degree centrality is that it divides the degree of a particular node by the total number of nodes minus one. Okay, so let's check out this graph. Basically, this is the graph that we. Yeah. So as you can see here, 4 is connected to, let's say, 1, 2, 3, 4, 5, all the rest of the nodes. So its centrality is higher, okay, than the other nodes. So let's say 6 is just connected to one node, then its centrality score is low. All the nodes with degree 1, they are like very less centrality. Okay, so 6, 5, 3 uh, are those nodes, right? Then 2 has degree 2 and likewise 1. So they have same score. Okay, 0.4, 0.4. So this is called, this is a local measure because the score that 4 gets is uh, based on its immediate neighbors. It doesn't care what's happening in the rest of the graph. Okay, it just cares about the direct adjacency of the node itself. That's why degree centrality is local measure. Okay, we'll see how a measure can be non-local or take more information into consideration than just the immediate neighborhood. So a real life example of degree-based centrality would be, let's say that you have to choose a monitor in the class, right? And everyone in the class votes for the candidates. Okay, the more the number of votes that candidate gets, higher is its score, right? So it's dependent on the direct votes that a person is getting, right? Which is quite similar to the direct neighborhood of a node in this graph. So that's the degree-based centrality. Second class of centrality is closeness centrality. Okay, so closeness centrality, what it takes into consideration is uh, it relies on shortest paths of the node with other nodes. Okay, so let's develop this graph, right? So what closeness centrality will do is it will divide the length of shortest path of each node with the rest of the nodes. Okay, so let's say that if we consider 3, right? So 3 is the path between 2 and 3, the shortest path between 3 and 2 is of length 1. Likewise, 3 and 1 is also 1, right? 5 is also 1, and 6 is basically 2. Okay, so when we sum the all the shortest paths, we get a number, right? And more that number is, less important the node is, right? Because we want a node which is closer to all the other nodes to be more important. So that is reflected in the formula itself. Uh, we sum the shortest paths, length of shortest paths of that particular node with all other nodes. And since it is inversely proportional to that, then the lesser the sum of distance, shortest path with the node, better it is for the node, right? So that is the closeness centrality. Uh, Example could be, in an office, if you want to spread some communication or message, then it's better we ask the person who is very well connected and closer to a larger group, right? So a manager who is centrally located in terms of communication might have high closeness centrality, and if that person passes the message, then it will reach, or that information will be disseminated to the wider population faster. So that's the real life example of closeness centrality. Uh, Third kind of centrality is betweenness centrality. Okay. So there we are not exactly interested in the length of the shortest path, but we are interested in that in a graph. Let's say we want to pass an information from one node to another, right? Then we'll consider all the shortest paths uh, of that particular node with all other nodes. Okay, and we'll assign higher importance uh, to the node that occurs in the most shortest path. Okay, so that's how betweenness centrality is calculated. Here we can say that 6 has the highest betweenness centrality because it's kind of a necessary component that people will have to go through in order to reach from, let's say, 2 to 3 or 4 or 5, right? So if you remove 6, then there is no easy way to go. There is no way to go from one node to another, right? So the importance 6 is getting here is because it lies in the most number of shortest path, right? From 2 to 3, 2 to 4, 2 to 5, 6 is important, right? Likewise from 1. The only shortest path 6 isn't part of is between 4 and 5, 4 or 3, 1 or 2, right? So that's why 6 has the highest centrality. Uh, Node number 1, 2, 3, they have 0 because they doesn't lie in the shortest path uh, of any node. between any two nodes. Okay. Likewise, 4 is a part of shortest path between 5 and 3. So that's why it has some importance. But other than that, we don't see uh, much of importance given to the nodes. So this is the betweenness centrality. Betweenness centrality comes into picture when we look into the bottlenecks between the information flow or traffic, right? So let's say that uh, there are some junctions on the road which most people cross when they are optimized for the least distance from one place to another, right? Let's say a bridge or some junction, which see high traffic. We can actually calculate that based on betweenness centrality. Betweenness centrality is also known as shortest path based centrality because all it cares about is what is the shortest path between two nodes. Okay, there may be some other paths which are not shortest, but betweenness centrality doesn't care about those uh, paths. Okay, now comes feedback based centrality. Okay, so feedback based centrality can think of it in terms of influence. Okay, I'll give you an example. Let's say I am on Twitter, you are also on Twitter. I have 5 followers, you also have 5 followers, right? But so the degree of me and you is same. Okay, but it may be possible that one of the people who follows you is very influential. Okay, or let's say that one of the people who follows you is actually followed by some very influential people person. Okay, then our centrality algorithm should be able to assign higher score to you than me, because even though we have same number of followers, but you are being followed by more important, more influential people, right? And there should be some way to transfer that influence from those people to you, irrespective of the degree. Okay, so that thing is taken into consideration by feedback based centrality measure. And this eigenvector centrality is one of those feedback based centrality measure. And you can see here in the example, let me just refresh it so that we can, yeah. So here you see that 3 and 5 have degree 2 and 4 also have degree 2, right? But 4 is able to gather more importance, right? Because it is directly being followed by influential people who are being followed by other people, right? So that's why even though their degree is same, which is 2, one of them is able to gain higher importance, right? Because of the quality of people or influence of the people who are following this node. Okay, so this is feedback based centrality measure. The measure that we are going to study, which is PageRank, falls into this category, and we'll get into deeper into its detail the next part of this talk. So, is there any doubt so far what we have discussed? Okay, so now let's discuss PageRank. Okay, so just a little history of PageRank. So PageRank was developed by Google founders Sergey Brin and Larry Page, and their use case was to assign importance to web pages. And web pages are kind of an example of a graph only, where if a page is linking to another page, right, then we can draw an edge from that page to another page, right? So we'll delve deeper into the mathematics of how PageRank was developed, right? And then in the next part, we'll discuss its application on text. So as we earlier also discussed that what is the nature of direct graph, right? So directed graph has edges, and 3 is pointing to 4 doesn't mean that 4 is automatically also pointing to 3, right? They are separate. So edges are basically the ordered pair. 1, 2 is not same as 2, 1. So this is a directed graph, and now we'll dwell into some linear algebra that we can apply on graph to get some interesting properties out of it. So how do we represent a graph in terms of a matrix? First thing that comes to our mind is adjacency matrix. Adjacency matrix is basically, let's say our graph is has n vertices. Okay, so adjacency matrix will be an n cross n matrix where if there is an edge between the two nodes, then that uh, particular cell will be 1, otherwise it will be 0. Okay, so if you see here, there is an edge between 1 and 2. Okay, so there is an edge between 1 and 2. So this node is basically uh, 1. Okay, uh, there is an edge between 1 to 3 and 2, right? 3 and 4. So this is the case, right? So wherever there is no edge, the value is 0. Okay, now as a directed graph, then it is not a symmetric matrix. Okay, if there was, if it were a undirected graph, then if there is an edge between 3 and 4, then there would have been an edge between 4 and 3 also, right? And we would have gotten a symmetric matrix over there. But in case of directed graphs, we get a matrix that is not symmetric. Okay. Now, there is an interesting property that adjacency matrix have, uh, which is how they can represent can be reached from one node to another, right? Uh, that is represented by adjacency matrix. So uh, let's say I raise a to the power 2. Okay, then what I get is this matrix. Okay, which will again be n cross n matrix. And now the ones in this matrix will tell me which nodes are reachable if I draw a path of two length between them. Okay, so 1, 2, 3, 3 and 4, right? So we can see that node yeah, so node 4 and 2, right? I can reach from node 4 to 2 via path of length 2. Okay, likewise I can reach the node 3 and 1 and yeah, so let's look at how this is being represented over here, right? So we have two ones over here, and basically there are two pair of nodes which are reachable by a path of length 2. Okay, so this is represented by a to the power 2. Likewise, if we do a cube, then there is only one pair, which is node number 2 and 3, which is reachable by length of path of length 3. Okay, so 3 1 2 3, right? So I can from path node 3 to 2 via path of length 3. Okay, that's why this is the only one we will get in a to the power 3. And when we raise a to the power 4, all of them are 0, so there are no uh, paths between nodes of length 4. Okay, so that's the interesting property we get just by raising the adjacency matrix to different powers. Now, how can we define connectedness of a graph via this? So let's go through two definitions first, and then we can discuss how we can formulate it in terms of adjacency matrix. Okay, so a graph is said to be connected graph if either node I is connected to J or J is connected to I. Okay, we don't care about definition here. If there is a directed path from either from I to J or from J to I for every pair of vertex in the graph, then we can say it's a connected graph. Uh, when do we say a graph is strongly connected? When infinite number of steps we can reach from one node to another. Okay, so I should be able to reach from any node to another node uh, by following finite number of steps across the directed edges. Okay, and if every pair is connected like this, then that graph is strongly connected. Okay, and how do we formulate the strongly connected graphs in terms of adjacency matrix? Uh, we define a matrix B, okay, which add all the powers of adjacency matrix. So this will be a to the power 0, a, a square, a cube, likewise ak, right? And if you are able to get a matrix B by adding the powers of A to a finite number k, such that B is all positive numbers, all are non-zero positive numbers, then we can say the graph is strongly connected. And what does it imply is that within k steps, any node will be able to reach the other node. Okay, so that's how we represent strongly connected graphs in terms of the adjacency matrix of a graph. So the next interesting matrix that we have around graph is transition matrix. Okay, so what does transition matrix means? I'll show you with help of a figure. So, and then we can go through the definitions. So, let's say that I have a node 1, right? And it has three neighbors. So, 2 is the neighbor of 1, 4 is the neighbor of 1, and also 3 is the neighbor of 1, right? So, if I have three neighbors, that I can choose to jump from here to any of these three. Okay, so we assign probability to these edges. Like, what is the probability that if I decide to jump from here, uh, I'll jump to 2, right? And that probability is calculated by dividing uh, this edge by the degree of 1. So degree of 1 is 3. If I divide 1 by 3, then I get 0.33. Okay. Likewise, if you can say 3, right? 3 has only one outgoing edge, which is 2, 1. Okay. So here the probability of me jumping from 3 to 1 is 1 because I don't have any other option. So transition matrix basically deals with the probability which would jump from one node to another in graph. Okay. Uh, so formal definition looks like this. We have n cross n cross n, and each cell is 1 by degree of I if there is an outgoing edge from I to j. Otherwise, it will be 0. So that's what transition matrix looks like. So this is what transition matrix have. What this means is that node number 1 has 1 by 3 probability of jumping to 2 3 or 4. Okay. Likewise, node number 3 has probability of 1 from jumping to 1, and rest are 0. So this is what transition matrix is, and in the remaining section, this will be important. Okay, so we'll discuss some properties that a transition matrix have, properties and limitations. So one of the property that this transition matrix hold is Markov property. Uh, Markov property means that my future depends only on my present, independent of how I reach the present. Okay. So in this graph, if I show you, then my probability of jumping from 3 to 1 is 1. And it is independent of how I reach 3. I would have reached 3 from 2, or I could have reached the node 3 from 4 also. Okay. But my probability of jumping from 3 to 1 is 1. And it's independent of how I reach there. So transition matrix shows Markov property. Okay. Uh, there are two definitions of matrix. Uh, One is primitive matrix. Okay. Primitive matrix is how do I say? A matrix is primitive if any node reachable from other node in finite number of steps. Okay. If that's the case, then the matrix is primitive matrix, and that graph is fully connected. Okay. Uh, Third definition is basically of stochastic matrix. If all the values in a column adds up to 1, right? So here 1 by 3, 1 by 3, 1 by 3, 1, 1, 1, 1, right? So we can say this is stochastic uh, matrix, and it is obeying the law of probability, right? So it's not there is no node I can jump from which has probability greater than 1, right? That's one thing. And sum of all the probabilities with respect to one and its neighbor is 1. Okay, so that's what we mean by column stochastic matrix. If rows add up to 1, then we say that it's row stochastic matrix. But as far as transition matrix is concerned, we'll be interested in column stochastic matrix. So we have already seen a graph, right? And this is a function to test whether a matrix is primitive or not. Okay. So what we do is we separate the number of the powers, right? So just like powers of adjacency matrix has a meaning, transition matrix also have a meaning, right? So e to the power 1 tells me that what is the probability of reaching 2 from 1, right? Directly. Now, if I square the transition matrix, then what it will get me is what is the probability of me reaching from one node to another via two-step path, right? So that's the meaning of powers of transition matrix. Okay, and if there is a finite power that gets me to all the positive numbers, then what does it tell me is that every node is reachable from every other node via non-zero probability, right? So this thing a to the power 3 gives me all positive cells, which means that I can reach every node from other node uh, with at max 3 steps. Okay, so that's what primitive matrix uh, means, and that's how it is implemented with the help of transition matrix. Uh, any doubts so far? Okay. Am I audible? Hello. Okay. So let's resume. So now we'll talk about stationary distribution. And to talk about stationary distribution, uh, let me give you an example of a surfer. Okay. Uh, what a surfer does is it starts from a random node and obeying the transition probabilities, it jumps from one node to another. Okay. So let's say with a tick of a screen, right? It jumps from one node to another. Okay. So I'm at four, uh, and I'm that surfer, and I have two options over here, either to jump on one or two, right? And I pick randomly pick one, jump on two. Then another time step, I jump on, let's say, one of the two nodes that are reachable from two. Another time step, I jump from three to one, right? And I keep on jumping at each step from one node to another. Okay. Now, what stationary distribution tells me is that that surfer is jumping right from one node to another, following the transition probabilities. Now, if I look at this graph, I observe that surfer at any point of time. What is the probability that I'll find that surfer on one of these nodes? Okay. Now, that thing is represented by stationary distribution of a matrix. Okay. It is a long-term behavior of the Markov chain that is described by the graph, okay, or by the transition matrix. Okay, so even though they are like different probabilities, I can jump from here, but overall they converge, right? And I can roughly guess where surfer is to be found more if I randomly look at uh, surfer jumping from one node to another, right? So here we can say that three has three incoming edges, right? So we can roughly guess that there is higher probability that a server is to be found here. Okay. Likewise, there is only one way that a server can jump to one, which is from three, right? So we are developing rough intuition that probabilities will be high where there are more incoming edges. It will be less when where there are less incoming edges. Okay. So how do we find stationary distribution? First of all, for a stationary distribution to be unique and useful, it should follow two properties. One, the transition matrix should be primitive, and another is it should be column stochastic. Okay, so this is a graph on which we'll calculate the transition stationary probabilities. Okay, now how can we calculate the stationary probability or long-term view? There are different ways. One of them is treating the transition as dynamic system of systems. Okay, so how we'll frame this problem is like this. Okay, at each we assign some importance to each of these node, right? So here we have one, two, three, four nodes. We assign 0.25 importance to all the nodes. Okay, and now each step, what each node will do is it will give its importance to its neighboring node. Okay, so let's say it has 1 by 4 importance at this point. It has three neighbors. So what it will do is it will distribute its own importance equally to all its neighboring nodes. Not only it is doing that, it is also receiving importance from its neighboring nodes. Okay, so that's what power method does. Okay, we start with the importance random importance, which is 1 by n. and then keep on distributing step by step, right? And then we see when it is converging, right? There will come a point where at point t I have some importance, and at point t plus 1, after giving and receiving importance from my neighbors, my importance doesn't change. That is the point of convergence. Okay, so this method is called power iteration method, and how it is implemented is that uh, we start with uh, random probabilities, which is 1 by n, then keep on multiplying, you know, with the transition matrix, and then wait for when it is converging. Okay, so if you run it on this matrix, the final stationary convergence would be this. Okay, uh, roughly what we are seeing here is that one is the most important. Okay, uh, third is important, then fourth, and then least important is two. And if we see here, uh, you can say why one is more important, right? One has a degree of 2, right? And it's one of the neighbor is actually is taking importance from three different people, and it doesn't have any other choice to give its importance to person other than one. So even though 3 has degree higher than 1, which is 3, 3 has 3 degree, and 1 has only 2 degree, right? Still 1 ends up with higher importance, because not only it matters that which people are adjacent to me, what also matters is how important they themselves are. Okay, and that is reflected in the final stationary distribution that I get for each node. Okay, each number here determines or tells me what is the probability that if I randomly put a surfer, you know, where the surface is lying uh, at that particular node, right? So if I randomly look at the surfer state, then there is 0.38 probability that I'll find that surfer on node 1. Okay, and 0.13 probability that I'll find that surfer on node 2. Uh, is it clear? Power method. Okay, so that's one way to look at it. Second way, how we look at it is we solve it algebraic way. Okay, so we are interested an importance vector pi, which when multiplied with transition matrix won't change. Okay, and this thing is solved by using eigenvectors. Uh, this is when we solve for eigenvectors, the eigenvalue 1, right? Pi p is equal to 1 into pi. So if I find the vector corresponding to eigenvalue 1, that vector is going to be my converged stationary distribution. And if I apply the same function, I get roughly same stationary distribution as I got from power iteration method. Okay. So connecting it with the previous section, we talked about how feedback centrality takes into consideration not only the immediate neighborhood, but also the influence that the neighbors carry. And it is like cumulative influence that is flowing into neighbors, the neighbors of neighbors, right? So it's more holistic and more accurate picture when we talk about uh, graph that gives more importance to influence. Okay, so that was about how do we calculate stationary distribution via transition matrix to get a more holistic view of how much importance each node holds. Now we delve into PageRank and how it was devised and the problems that we faced in simulation. How do we solve it? Okay. Now, the stationary distribution that we calculated on transition matrix, these transition matrices are well behaved. Well behaved in the sense that they follow the two necessary conditions, which one of them is they are additive, that is, each node can be reached by another node in finite number of steps. Okay, so it's additive. And second is it follows the laws of probability, that every column adds up to one. Okay, so that's the behavior of the matrix that we played with, and that's what is the stationary distribution, unique stationary distribution. Now, if we apply the thing in WebGraph, uh, these things doesn't work. Okay, first of all, we use the following formula. Let's say that a web page has an outgoing link to some other page. Then we draw an edge from that particular page to another page, right? So, and the graph that is the result of that, we call it a web graph. Now, web graph have some problems. One is dangling nodes. So, it is very well convenient to have web pages that don't point to any other page. Okay, so such nodes are called dangling nodes. So we can see that one is pointing to B, two is pointing to three. Now, if my surfer jumps from one to three, it won't have any other place to go. Okay, so from the path charted by the surfer, this means a dead end. A surfer would never be able to get out of it, right? And if we think of it from dynamic systems point of view, then tree would never be able to give or share its importance with any other node. Okay, so that's the consequence of dangling nodes. They are also called sinks, since they take in all the signals, but nothing goes out of them, right? So that's one problem that WebGraph faces. Second is disconnected components. It is very well possible to have components in graph which have no relation, right? So our web graph will end up with elements like this. Okay, so these are like two web pages. One is pointing to two. These are like another set of three pages where they are pointing to each other, right? Likewise, there will be a lot of disconnected components in web graph, and these two things will prevent us from calculating stationary probability vector ever, right? So how do we solve it? So what how Google people solved it is they proposed a way, Google metrics. Okay, so first problem is that there are sinks which doesn't point to any other node. Okay, and second problem is of disconnected components. Now we want to modify the transition matrix in such a way that it doesn't adulterate the relative importance, okay, of these nodes. Okay, uh, हमारा सोल्यूशन से ऐसा नहीं होना चाहिए कि जो नोड उतना इंपॉर्टेंट नहीं होना चाहिए था वो इंपॉर्टेंट हो गया, राइट? So we need to manipulate this transition matrix in such a way that the relative importance uh, isn't adulterated, and our transition matrix follows those two properties, right? So how do we do that is first we handle syncs. What we do with syncs is, let's say that one is pointing to 2 and 2 is not giving its importance to anybody else, right? So we draw an edge from 2 to every other node in the graph. So as a result of that, what will happen is that earlier we had this row of all zeros, right? Now for sync, what we'll have is uh, we'll have 1 by n, 1 by n, 1 by n, and this row will become stochastic in nature, right? So we handle all the syncs this way. So all the syncs get to give the importance equally to every other node. Okay. Now the second thing is uh, disconnected components. Okay. So these components are not connected, and the solution that we have via calculating stationary distribution. So this graph is disconnected, and we calculated eigenvector anyway. Okay, and we got a stationary distribution. Now what the stationary distribution did is it uh, gave us a clear cut relative importance of these three nodes, okay, which is 1 by 3, 1 by 3, 1 by 3. Totally ignored this. And there will be some other eigenvector which will assign importance to these nodes, but won't take these into consideration. So this disconnected component needs to be handled, and this was handled by allowing the surfer to jump, randomly jump from in between disconnected components. Okay, so what we did was, this is how we handled the sinks and disconnected components. What happened is that we came up with a damping factor, which is alpha. Okay, so alpha is the probability that at any time step I'll obey the rule of probability and jump to the immediate neighbor of that particular node. Okay, and 1 minus alpha times what I'll do is I'll jump to any other node in the graph with equal probability. Okay, so this is a get Google matrix function where we take a node, we devise a transition matrix, and then we fix the dangling nodes and disconnected components. Okay, how we fix the dangling nodes? We assign 1 by n weighted outgoing edge from sync to every other node. And how we handle disconnected components? We add another matrix E to the original matrix. Uh, and as a result of what happens is there are no more disconnected components. Okay, because we have given the surfer a way to jump from one disconnected component to another. Okay, so ideal value for that damping factor is 0.85. What does this mean? 0.085 प्रोबेबिलिटी के साथ सर्फर जो है अपने इमीडिएट नेबर्स पे जंप करेगा, और 0.15 प्रोबेबिलिटी के साथ वो ये नोड छोड़ के पूरे ग्राफ में किसी भी नोड पे जा सकता है, राइट? एंड एज अ रिजल्ट ऑफ दैट, what happens is the matrix that we get is column stochastic and primitive. Okay, and now we can calculate. So now what we are doing is we calculate the page rank of the disconnected graph only, and as a result of this, the stationary distribution that we are getting, right? So these are three are equally important, and there is some more importance to two, right? So even though the graph is disconnected, we are able to calculate the importance of each node in this web graph by cleverly handling the two problems that we were facing. One was of sinks, another was of disconnected components. So that's how PageRank was solved the problem of assigning importance to a web graph, which is by nature disconnected and sparse. Uh, do you have any doubt in this explanation?
Hey Ankush.
Hi.
Yeah. So first of all, thank you.
So,
It's difficult to like include everything about PageRank in one discussion, but I have one quick question. So
yes,
PageRank also considers the random surfer model, right? So let's say if I'm
yes,
reading a news article on Times of India, I will not keep
yes,
on clicking hyperlinks indefinitely. All the hyperlinks within the Times of India. So at some point, I'll just close the tab and start something like
yes.
start working on something else, right?
Right.
So, yeah, so that is applicable in the internet scenario, web. But do you think the same thing can be applicable in the language? Like,
Okay.
because if I have to
So I'll
communicate something to you, I'll do it completely, right? I'll not think about the words. So this word links to this next word and something like that.
yes. So let me try to answer this question in terms of how this thing solves web, and then what is my interpretation of what role it plays in language. Okay. So here we implement random surfer model via this damping factor. Okay,
Hmm.
0.85. So
Yes.
0.85 times I'll just follow the links, and 0.15 times I'll jump to another node. Okay, that's one importance of this. And here E is uniform, right? 1 by n, with 1 by n probability, I can jump to any other node when I decide to jump and not follow the link. Okay, and here what the role E plays is we can actually use it to create personalized ranking, right? So let's say that if I am a sports enthusiast, then I am more likely to stop following the link and then jump to some random sports page. Okay, and how I can this ranking personalized for a sports lover is that I'll assign more probabilities uh, in this matrix to sports related pages, such that they still follow the laws of probability, but now I have more probability of jumping to that sports related page.
Yeah, yeah.
Okay,
Basically, you are
so
increasing the number of
that's
dimensions. Yeah.
I'm actually decreasing the probability of not non-sports page. I'm increasing the probability of sports page, ensuring that they sum up to one, right? And I'm more inclined to. I want the user to make the jump to sports related page, right? So that's what the interpretation of random server model is in this PageRank. Okay. In text, let me do one thing, Raj. Let's discuss the text graph first and different variants, right?
Mhm.
And then I'll discuss the interpretation of what random surfer model can do
Yeah, yeah.
over there.
Sounds helpful. Yeah.
Okay.
Thanks. Yeah.
Okay. Cool. So just a quick recap. We first went through graphs, discussed networkx, different centrality algorithms. We applied it, whatever functions that were given in graphs over here. Then we dwelled deeper into the mathematics of PageRank, uh, how uh, how centrality is calculated via matrices, by applying linear algebra. Uh, what are the properties, adjacency matrix, transition matrix, what are their significance, and the power of adjacency matrix, powers of transition matrix, what do they imply? Okay, how they are used to represent the connectedness of a graph. Then we discuss the web graph, uh, how links are represented in a web graph, and what are the problems that we face there, which prevent us from applying eigenvector based methods on the web graph. Then how do we solve it? Okay, and how do we get Snell distribution out of something non-behaving graphs like a web graph? Okay, now we'll dwell into NLP and how these algorithm can be used in text. Okay, so let's first talk about spacy. Spacy is a NLP library that have a goal to provide production ready modules to NLP practitioners. Okay, so that they don't have to implement things from scratch. So whatever new algorithms comes in NLP problems, Spacey people actually train good enough models, and that solves the problem of, let's say, 90% of NLP practitioners. Okay, decent enough accuracy and speed, and they are able to use it directly. Uh, so let's start with this. What are all the different things that Spacey help us do? Okay, so what Spacey does is it takes so you can import it directly, like import Spacey, and then you can actually load a model. This is a statistical language model which Spacey people have already trained, and when you load it, you get a module NLP. Okay, uh, here N core web SM means SM means small. If you want more accuracy, but you are able to compromise on speed, then there are two other models: Encore Web MD, Encore Web LG. Okay, so for demonstration purpose we use small model. Now when we pass text to this NLP module, it returns to us a doc object. And let's quickly look at what are the different things that this doc object helps us do on text. So one thing is basically it help us detect sentence boundaries. So let's say that I have a this text. Just, yeah. So I have this text, right? It has multiple sentences. We can think of it as a paragraph. Now I can loop over different sentences of this text uh, via doc.sense. Okay. So this NLP module broke this text into different sentences for me. Okay. Not only that, it also gave me indexes of the sentences. Okay, send dot start is 0 and 13. What it means is that this sentence starts from 0th word and goes till uh, 13th word, 12th word. Okay, or 12th token. So sentence boundary detection is one. Second is tokenization. By I can actually loop over the different tokens of a sentence uh, by this, right? So it has different properties. So one is compatibility is the word. So text is as it is. It will lemmatize it. So lemmatization sometimes break the word into smaller word. Sometimes it just lowercase the words, right? So in this case, it is lowercase. It will give me the pause tag, which is a noun. So this word is noun. It will tell me whether it is an alphabetic word. If it contains anything other than alphabet, then it becomes false. It tells me whether it is a stop word or not, right? So compatibility is not a stop word here. Likewise, off, it's a stop word, right? It's an alphabetic character. It's a pause tag is ADP. Off is basically, I'm not able to recall the exact pause tag, but I can loop over all the words and I can get all the linguistic properties out of each words or token. Okay. Uh, so that's another thing I can do with Spacey. Named entity recognition is another thing I can do with Spacey. So let's say that if I do doc.noun chunks, then I'll get all the noun phrases that this doc has, right? So compatibility, systems, linear constraints. So linear constraints is like two tokens. When they are together, they make sense as a noun chunk. Okay. So these are the different things Spacey helps us do. encourage to go through the documentation, and there are not many other things that spacy does, like the properties about sentence, tokens, phrases, adjectives, uh, which are definitely worth checking out. But for the sake of our discussion, I think this much capabilities of spacy are enough for us to continue. Uh, let's talk about text rank algorithm. Text rank algorithm in 2004, NLP group came up with text rank, where they applied rank algorithm on text. Okay, and gave a good enough baseline for tasks like key phrase extraction and summarization. So text rank is a graph-based, unsupervised, unsupervised because it doesn't need any training data. And for key phrase extraction, extractive summarization. Why extractive summarization? Because any summarization that text rank do, it will come out of the original text only. It won't uh, add its own text in the result summary. Okay, so what are the steps that they gave in the paper for creating a text rank? So define what our voices are going to be. So in our case, we will define our notes as we summarize and we so each of our nodes or vertex will look like a tuple of lemma first. So that can be common now because one vertex in our text graph. Why do we use lemma? Because we want different variations of the same word to enter one node. So let's say that if we have a shorter word, let's say we have a word dog, okay, and we have dogs. Okay, we want these both words to enter one node, a single node. That's why we'll use lemma of the word instead of text as it is. Okay, and we also make it more unique by also using cross tab of that particular. How do we create edges or connect the nodes? So currently we do a sliding window uh, on our text. Okay, and if two words falling in the window of, let's say, in the same sentence, join between the words. Okay, so that's how we define the edges. And once we have on the graph based on the definition of nodes and edges, we apply the region. Okay. And then we create an edge. Okay. So that's what we do over here. How do we link sentence? So link sentence function it does is it loops over a sentence one by one, and if two words falling in the window of three, it is creating an edge between the two. Okay. is ending, another is beginning. Those two words will fall into the same window, but we don't want to draw edges between them. Why? Because they are following in different sentences, right? That's why we draw the edges sentence by sentence. So this function does that. Next thing is that we don't want to create nodes out of all the past tags. Okay, so we just take into consideration nouns, proper nouns, verbs, and adjectives, and use them as nodes. Okay, so when I do this, when I've drawn a graph, and when I run pipe, each word is getting. Okay, I can also draw a graph where the size of the score that token has, right? So here we set, solution. These have like slightly lower score. Likewise, there are other words which have even lower score, right? So quick recap of how we calculated it. We looped over the text sentence by sentence and draw edges between the nodes that were falling into a window of size 3. And as a result of that, we got a graph. Okay, and then we just calculated the page rank over that graph, and we got the importance of each. Next thing is basically key phrase extraction. Uh, it's not keyword extraction. Top key phrases. Uh, that is what we are going to look into. So spacy. Okay. Then first thing is okay. Rank is here score. Uh, so we get a rank sum. Okay. And now what we do is uh, we take a root mean square of the rank sum. We normalize it by the length of uh, the noun phrase, which is chunk length. Plus, we also punish it based on how much non-lemma scores, non-lemma word of phrase Tower of Hanoi, right? Now, Tower of Hanoi will be a noun phrase, but here Tower and Hanoi, these are like noun chunks, and off won't be finding itself in the graph. So we'll punish Tower of Hanoi because of the non-lemma word that is in this, in that, right? Let's say we have another noun chunk where all the three words are actually participating in graph also, then it will get slightly higher score. So that's what this second step does. And then we further words in it, right? And finally, what we get is phrase rank of the word scores that that phrase had. Okay, so here we had compatibility to the one word phrase, so it got the score as it is, right? Linear constraint is another. Uh, this is the cumulative score based on the linear and constraints. So that's how we move from word scores to phrase scores. About different variants of text rank, and after that we'll take the question of what role does damping factor or random surfer model have over here. Okay, so there are different variants of text rank. PyText rank is the spacy extension which we have. Just a minute, yeah. So what it does is, rather than it masks away, abstracts away all the graph creation and everything, and provides a neat interface of applying text rank on text as a spacey pipeline. So if you see how PyText rank work is, we just have to import this module, and we add this pipe in the existing pipeline, rank phrases. Okay, so if I do this, this text added text rank pipeline over here, and when we do doc.phrases, their score. Okay, this is a simple base model. Another variant is biased text rank. Biased text rank is what we just discussed, how we apply personalization in text rank. Okay, so when we apply base text rank, uh, user doesn't have any preference about what things he is more interested in, and whatever page rank we are getting from the graph, we end up with the scores. Okay, now user may be interested in certain parts of the text. So what user can do is, so we can add another pipe, bias text rank, in the NLP, focus. So this is a football article, and we are saying that we are specifically interested in Leicester, right? This is I think team's name. So when we change our focus over here, then we are actually favoring the words or phrases that lies closer to this. Okay, so that's how bias text rank work, and how it is works under the hood is by changing the e matrix, right? So we saw over here that we have two matrices, right? This is the actual transition matrix. This is the random matrices, where the user can follow the links but jump somewhere else, right? So we manipulate this and give higher score to our focus words. Okay, and as a result of that, what happens is that the words around focus and the focus words randomly jumped upon, right? And as a result of that, the so this is called biased text rank. This was implemented in the recent 2020 only, same group. Okay, so this was about biased text rank. Another thing is position rank, right? So all these variations of text rank, they play with the random start matrix that is added, right? So in position rank, what we do is, every word has a location. It favors those words in the document. Okay, so that's why it's called position rank. So let's say a word is occurring, what we'll do is 1 by 2 plus 1 by 50, right? And then place it in the personalization matrix. And as a result of that, what will happen is words that are occurring earlier in the text, they end up being favored. So this is same text but with position rank, and we see that systems is occurring early in the text, so it is being favored, right? Minimal generating sets, all these things are ending on the top, right? So set is on top, so the set ends up on top. So this is the variant where we favor the position. Then there is another variant, which is topic rank, right? So uh, topic rank manipulates the personalization matrix by clustering the words into certain topics. And then the graph, which was earlier made on the words, is now made on the topics. Okay. And PageRank is calculated on the topic graph. And then the most important topics are picked up, and then words are sampled from there, right? So this is again the football article. And when we do topic rank on this, then we get a totally different list out of there. So topics that are more prominent gets higher score, and then words are picked up from those topics only. And based on that, a new rank list is produced. So a quick recap. We talked about spacy, how it provides different linguistic properties on text and how we can use them in our implementations. We talked about text rank algorithm. How do we form a text graph by looping over the sentences and connecting words that fall into a window of certain size. We talked about how we apply PageRank on, on that text graph and get word scores. We talked about how we move from word scores to key phrase scores. And then we talk about different variants of text rank. Now, to answer your question, Raj, uh, here random surfer model, the role that it plays, right? Uh, we are taking a window size of 3 here, right? So we have a window size of 3. Now, if we don't consider the random surfer model, then first thing is we might get a disconnected graph, right? So one necessary thing why we want to use that same equation here is to solve that problem. And let's say if our graph is connected, but we don't want, let's say our graph is connected, but still the importance will take time to flow from one node to another serially, right? And when the text is long, there may be lot of important themes around that text, and we need a way to jump from from one theme to another without having serially going through one node to another, right? So that's why, like, it makes sense for us to have 0.15, like same notation over here, so that we can jump from one theme to another without having to traverse the node from one place to another.
Got it. Yeah.
Okay, cool. Is there any other doubt?
Nothing from my side. Yeah.
Okay, so what I'll be doing is